Imagine you're sitting in this sleek, glass-walled conference room, right? High up above the city.
Oh, a classic finance setup.
Exactly. And you're holding a pitch deck for this newly developed algorithmic trading strategy. The researcher sitting across the table from you is just projecting absolute certainty, like total confidence. And honestly, looking at the numbers printed on that heavy stock paper, their confidence seems completely
Mhm.
justified.
Because the back test looks amazing.
Oh, it's aggressively beautiful. The strategy boasts a massive 2.33 annualized Sharpe ratio. Now, for anyone who's spent time analyzing financial data, a Sharpe ratio north of 2.0 is just staggering.
Right, it's almost unheard of in the wild.
Yeah, it represents a return profile so smooth, so consistently profitable relative to its volatility, that it basically looks like a guaranteed money printer. It's the kind of equity curve that practically demands immediate funding. But, and this is the crux of it, the reality lurking beneath that specific 2.33 Sharpe ratio is profoundly disturbing.
Very much so.
Because despite how mathematically pristine that backtest appears on paper, there is a 63% chance that this exact strategy will begin losing money the very second it goes live with real capital.
Yeah, and the scenario you're describing, it really represents the most dangerous blind spot in quantitative research today.
It's terrifying.
It is. Because the researcher across the table, they likely aren't trying to con you. I mean, they have genuinely convinced themselves that they've extracted a profitable signal from the market. But in reality, they've simply constructed this highly elaborate, mathematically disguised illusion. They've basically weaponized their own computing power to deceive themselves.
Wow. And so our mission today on this deep dive is to isolate and dismantle the mathematics of that exact self-deception. We're pulling our framework from a really fascinating, highly technical article by Sue Knott, which is part of the Backtest Without Illusions series. It's titled The Probability of Backtest Overfitting. Did your search beat a coin flip?
It's a fantastic piece of research.
It really is. And the foundation of this text is built on deterministic scripts that generate perfectly controlled mathematical environments. So basically, laboratories where the absolute ground truth is known before the test even begins.
Right, which is crucial because you can't test a lie detector on someone if you don't already know they're lying.
Exactly. And the goal here isn't just to equip you, the listener, with a new piece of financial trivia. We want to fundamentally alter the way you evaluate data-driven success. Whether you're analyzing a hedge fund's performance, or reviewing a medical trial, or, just looking at the results of a corporate A/B test.
Because the vulnerabilities we're going to expose today, they are inherent to the scientific method as it's currently practiced across dozens of industries. I mean, they strike at the core of how humans interpret evidence. We are just neurologically wired to seek patterns.
We really are. We see faces in the clouds.
Exactly. And when we apply massive computational power to large data sets, we will inevitably find patterns that look incredibly convincing, but possess absolutely no predictive value in the real world whatsoever.
Okay, let's unpack this. Under standard industry practice, when someone presents a winning strategy, like the one in our conference room, we usually put that specific winner on trial, right?
Yes. The final artifact.
Right. We look at the final top-performing configuration of the trading rules, and we apply statistical tools, like the Deflated Sharpe Ratio, to ask whether that specific return profile is statistically significant.
We try to price the winner to see if it clears a hurdle of probability.
But today, the source material forces us to abandon that framework entirely. We are not going to evaluate the winning strategy. We are going to put the act of picking the actual search procedure itself on trial. The scrutiny shifts away from the final output and onto the generative process that actually produced it.
And shifting that analytical focus from the artifact to the procedure, it fundamentally redefines the mathematical landscape. And it introduces a concept that runs entirely counter to basic statistical intuition.
This is the part that blew my mind.
Yeah. So the diagnostic tool used to measure this search procedure is called the probability of backtest overfitting, or PBO.
Okay.
And when you're calculating PBO, the null hypothesis, which is the baseline measurement indicating that your procedure has learned absolutely nothing that generalizes to the future, is 0.5.
Wait, so the baseline for total failure isn't 0?
No, it's not 0. It's not 1. It's exactly 0.5, half.
Which is so counterintuitive. That specific number requires some serious justification, because in almost every standard statistical test taught in a university classroom, the null hypothesis is anchored at 0. Like, we assume an effect size of 0, a correlation of 0, a difference of 0.
Right, and that ingrained expectation of 0 is exactly why PBO is so often misinterpreted by researchers. To understand why it's zero point 0.5, you have to look at the exact mechanical question. The probability of backtest overfitting was designed to answer.
Okay, let's get into the mechanics.
So PBO was formally introduced in a 2017 paper by a highly regarded group of mathematicians and quants Bailey, Borvine, Lopez de Prado, and Zhu. And they built this metric to interrogate the aftermath of a parameter sweep.
Let me define the parameters of a sweep for the listener real quick.
Yeah.
A researcher tests a massive grid of potential strategies, right? So different moving averages, different volatility thresholds, different entry and exit signals. They backtest all of them, isolate the single configuration that generated the highest historical return, and then they discard the rest.
Exactly. And the central question PBO asks is whether the selection of that single historical winner was a robust decision, or if the researcher merely crowned the luckiest configuration out of a massive field of random variables.
Like finding the luckiest person in a casino.
Bingo. To answer that, PBO measures a very specific transition. It calculates the probability that the configuration you selected is the absolute best during your historical backtest, what we call your in-sample training phase, ends up plummeting into the bottom half of the entire field when exposed to new, unseen, out-of-sample data.
So the metric is exclusively concerned with relative rank degradation.
Yes, entirely relative.
It's the probability that your gold medal, absolute best strategy during the backtest fails to even beat the median of all those discarded strategies once it hits the real world.
And that mechanism explains the 0.5 null hypothesis perfectly. Think about it. If a search procedure has genuinely captured zero real edge, if it has simply memorized the noise of the past, then the strategy it selected has no predictive power whatsoever.
It's just guessing.
Worse than guessing, really. When that strategy is exposed to future data, it is completely untethered from reality. It is just a random column of numbers.
And if it's a random column of numbers, its future performance is completely independent of its past performance. It could randomly end up in first place again, or it could end up dead last, or it could land exactly in the middle.
Right. Because its placement is entirely random, the laws of probability dictate that it will fall below the median ranking exactly 50% of the time.
Oh, wow. Okay, so it will land in the bottom half of the time.
Exactly. Therefore, a PBO of 0.5 mathematically defines a process that is functionally indistinguishable from flipping a coin.
So half doesn't mean partially overfit.
No. A reading of 0.5 means the procedure is entirely, hopelessly overfit. It's garbage. You want a PBO as close to zero as possible, indicating that the in-sample winner consistently remains at the top of the pack out of sample.
Let me give a practical analogy to help visualize just how absurd it is to ignore this. Imagine you host a coin flipping tournament in a massive auditorium. You invite 200 people and you instruct every single person to flip a standard quarter 5 times in a row.
Okay, I like where this is going.
Just by the sheer laws of probability governing a sample size of 200, someone in that room is virtually guaranteed to flip heads 5 times consecutively.
Statistically inevitable.
Right. Now, if you apply the standard Wall Street in-sample evaluation mindset to this event, you would identify that specific person, you'd bring them up to the stage, hand them a gold medal, and declare that they possess a profound, undeniable edge in the art of coin flipping. You might even build a pitch deck highlighting their flawless 100% win rate and raise capital to back their future flips.
And people would probably invest. But the moment the tournament continues out of sample, the moment you ask them to flip the coin for a 6th time with real money on the line, the illusion shatters.
Completely.
Their historical performance offers zero predictive power regarding the physics of the next flip. They are just as likely to flip tails as heads. They will immediately regress to the mean and fall back into the general population of the auditorium.
Exactly. And if you track their rank among the 200 participants in the next round, they will land in the bottom half exactly 50% of the time. Their PBO is 0.5.
It's a perfect analogy. The logic of the 0.5 baseline is undeniable when viewed through that lens.
But here's my pushback, or I guess the real-world problem. Identifying the flaw in the coin flipping tournament is easy because we control the rules of the game, and we can force the participants to physically flip the coin again. But in the real world of data science or quantitative finance, a researcher evaluating a 10-year data set cannot simply wait another 10 years for out-of-sample data to accumulate just to prove their strategy wasn't a lucky coin. Capital allocation decisions have to be made today.
They do. The evaluation has to occur entirely within the historical data that already exists.
Uh-huh.
which sounds impossible, right?
It does sound impossible. How do we test the future without waiting for it?
Well, the restriction of only having access to historical data requires a non-parametric engine to basically simulate the passage of time. We have to expose the fragility of the search process artificially, and the specific mathematical engine utilized to calculate PBO is called Combinatorially Symmetric Cross-Validation, or CSCV.
Combinatorially symmetric cross-validation. That is a mouthful. Okay, let's put this engine together. To understand how it processes data without relying on a time machine, we have to look at the raw material it requires. The researcher in our conference room has to feed a specific input into this engine.
Right. The singular input required by CSCV is a performance matrix, which we usually refer to as matrix M.
Okay.
To make this tangible, let's assign specific dimensions to this matrix. Assume a researcher has conceptualized a strategy and tested, let's say, n equals 200 different configurations or variations of the rules.
So 200 different moving average pairs or whatever.
Exactly. And furthermore, assume they tested these 200 variations over t equals 1,000 synchronous observations. In financial terms, this translates to 1,000 days of trading data.
Got it. So Matrix M is basically just a massive two-dimensional spreadsheet. It has 1,000 runs representing the chronological passage of time and 200 columns representing the daily returns of each of the 200 different strategies.
That's exactly it. And the construction of the validation process begins by manipulating the temporal structure of those 1,000 rows. Step 1 requires splitting the total time series into S equals 16 disjoint equal-length blocks.
Disjoint meaning the blocks do not overlap?
Correct, no overlap.
Okay, so dividing 1,000 rows by 16 yields roughly 62 rows per block, so about 2 months of trading days per block.
But wait, a critical point of inquiry here is the rationale behind keeping the data in intact blocks. Like, why chunk the data into 2-month continuous segments instead of simply shuffling the 1,000 individual days randomly? Because I know that's how a lot of standard cross-validation techniques operate in other fields of machine learning.
Oh, that is a fatal error when analyzing financial markets. Randomly shuffling individual days destroys the local time structure of the data.
How so?
Because financial returns possess memory. They exhibit autocorrelation and volatility clustering. Think about it. If a massive market crash occurs on a Tuesday, the volatility and trading volume on Wednesday will be heavily impacted by Tuesday's events, right? Right. The market doesn't just wake up on Wednesday with amnesia.
Exactly. The days are not independent. If you decouple Tuesday from Wednesday through random shuffling, you create a synthetic data environment that fundamentally violates the physics of the real market. By keeping the data in sequential intact blocks of 62 days, you preserve those critical local dependencies and ensure the simulation remains realistic.
Okay, that makes perfect sense. So we have the 16 solid blocks of preserved market structure. What's the next step? This is where the combinatorial phase comes in, right? The C and CSCV.
Right. The engine must determine how to separate those 16 blocks into a training set and a testing set. But instead of picking one arbitrary split, it chooses every single possible combination.
Every single one.
Every single one. You have 16 available blocks. The algorithm selects 8 of those blocks to serve as the in-sample training set. The remaining 8 unselected blocks automatically become the out-of-sample test set.
Okay.
If you calculate the combinations of 16 items taken 8 at a time, 16 choose 8, it yields exactly 12,870 unique ways to partition the data set.
Wow, that generates 12,870 parallel universes.
Basically, yes.
So in one universe, blocks 1 through 8 are used for training, and 9 through 16 are for testing. In another universe, blocks 1, 3, 5, 7, 9, 11, 13, and 15 are the training set, and all the even blocks are the test set.
You got it.
The sheer scale of this exhaustive partitioning, I mean, it stands in stark contrast to the standard industry practice, which is usually walk-forward optimization.
And walk-forward optimization, or WFO, is deeply flawed, precisely because it lacks this combinatorial symmetry.
Explain that difference for us.
In a standard walk-forward setup, a researcher takes a single privileged cut of the data. They might use, say, the first 5 years to train and the subsequent 5 years to test. They generate one historical verdict. The danger is that a highly overfit strategy, a jagged spike of noise, can easily survive one arbitrary out-of-sample cut just by blind statistical luck.
Because it's only being tested once at a sample.
Right. Walk-forward optimization gives luck a place to hide, but CSCV is exhaustive. By simulating 12,870 unique environments where the training and testing sets constantly swap positions and mirror each other, it applies an extreme stress test that a purely lucky configuration cannot possibly survive.
Okay, so with the 12,870 parallel universes constructed, the engine begins the interrogation process, and it treats each universe as an isolated simulation, right?
Correct. Inside every single one of those 12,870 splits, the algorithm analyzes the 8 in-sample training blocks. It ranks all 200 configurations based on their performance, usually evaluating their Sharpe ratio over those specific 8 blocks. It identifies the absolute best performer, the #1 winner of the training phase, which mathematically we denote as N star.
And because each universe contains a different combination of training blocks, the identity of N star is going to frequently change.
Exactly. In universe #1, maybe configuration number 42 perfectly aligns with the market conditions of those specific 8 blocks and emerges as the champion. But in universe number 8000, which uses a completely different set of 8 blocks, configuration number 112 might be the winner.
So the algorithm takes the specific in-sample champion of that particular universe, say configuration 42, and what does it do with it?
It evaluates its performance on the 8 held out-of-sample testing blocks. It calculates where configuration 42 ranks among all 200 configurations on the unseen data. It tests whether the champion of the training camp can maintain its dominance in the arena.
And this relative out-of-sample rank is recorded for every single one of the 12,870 splits. But how do we get a single number out of that? We have thousands of ranks.
To aggregate those thousands of ranks into a single interpretable PBO metric, the algorithm applies a specific mathematical transformation. The relative rank is converted into a measurement called a logit, denoted by the Greek letter lambda.
Logit, okay. Why not just use the raw rank?
The logit transformation is vital here. A relative rank is a bounded probability, right? It exists strictly between 0 and 1. If you try to run standard statistics on bounded probabilities, the math begins to distort at the extremes.
Right, because it hits a wall at 0 or 1.
Precisely. The logit function, which takes the natural logarithm of the rank divided by 1 minus the rank, solves this by mapping that bounded probability onto the infinite real number line. It stretches the scale, creating a perfectly symmetric ruler centered around 0.
So the symmetry around 0 is the key to interpreting the logit. A positive logit indicates that the in-sample winner landed in the top half of the field out of sample. It beat the median.
Right.
And a logit of exactly 0 or any negative number indicates that the winner failed to beat the median. It fell into the bottom half of the out-of-sample performance rankings.
You've nailed it. And to calculate the final probability of backtest overfitting, you take the distribution of those 12,870 logits and simply find the fraction of them that are less than or equal to 0. You are calculating the exact percentage of universes where the act of picking the best historical strategy resulted in out-of-sample degradation below the median.
Here is where it gets really interesting to me. What becomes immediately apparent when breaking down the mechanics of CSCV is an intentional, glaring omission. At no point in the generation of the parallel universes, or the ranking of the strategies, or the calculation of the logit, does PBO ever factor in the actual numerical value of the winning Sharpe ratio.
And never.
It does not care if the winning strategy has a Sharpe ratio of 0.5 or 2.0 or 10.0. There is no parametric threshold it has to clear, no p-value based on standard deviations.
And that omission is the source of its analytical power. PBO completely divorces itself from evaluating whether the strategy is objectively good or bad based on historical return metrics. It focuses exclusively on stability. It asks a relentless, structural question. Does the procedure of selecting the historical best generalize to unseen data? By evaluating the property of the search procedure rather than the property of the final strategy, it catches mathematical illusions that easily bypass standard metrics like the deflated Sharpe ratio.
Okay, so understanding the architecture of the combinatorial engine is necessary, obviously. But the theoretical framework means nothing if it cannot be proven to work empirically. Any diagnostic tool must be calibrated. You have to submerge a thermometer in freezing water and then in boiling water in a controlled laboratory setting to ensure it accurately reports both extremes before you can trust it to measure the temperature of a patient.
Naturally.
And the source text conducts this exact calibration using synthetic ground truth.
The calibration phase is non-negotiable. If you cannot prove the metric works on deterministic data where you play God and control all variables, you cannot trust it on noisy, chaotic market data. So the researchers built two distinct extremes to test the CSCV engine.
Let's start with the first test, the absolute freezing water, the null endpoint.
To construct the null endpoint, the researchers populated matrix M with 200 columns of independent, zero-drift, normal noise.
Pure static.
Pure statistical randomness. There is zero underlying signal, zero momentum, zero mean reversion. The true, fundamental Sharpe ratio of every single one of those 200 columns is identically zero. And to ensure statistical rigor, they didn't just run this test once. They ran the entire procedure across 60 different Monte Carlo-generated matrices and averaged the results.
So it's a field of 200 completely worthless random strategies. The search procedure is unleashed on this matrix. It evaluates the 200 columns and selects the one that performed the best in sample. And the resulting backtest of that winning column, this is the part that is just staggering.
The magnitude of the illusion is deeply unsettling. Selecting the best performer from a field of pure noise yields an average annualized in-sample Sharpe ratio of 1.98.
Wait, really? A 1.98 Sharpe ratio generated from nothing but static?
A bit noise.
To contextualize that for the listener, if a quantitative researcher walked into a major institutional hedge fund with a backtest showing a 1.98 Sharpe ratio over a statistically significant time frame, they would likely secure millions of dollars in capital allocation.
Without a doubt.
That profile suggests incredibly smooth, consistent returns with minimal drawdowns. And the text proves that this specific profile can be manufactured entirely out of thin air simply through the act of exhaustive searching.
It is the ultimate manifestation of selection bias. I mean, if you generate 200 random walks, statistical variance basically guarantees that at least one of them will randomly drift upwards in a smooth, highly compelling trajectory during your observation window.
So the search procedure didn't discover financial alpha.
Not at all. It simply located the luckiest column of noise and presented it as skill.
But the out-of-sample performance instantly exposes the illusion. When that 1.98 Sharpe winner is tracked into the held-out testing blocks, its performance completely evaporates. The out-of-sample Sharpe ratio collapses to 0.06.
It reverts completely to its true nature as a random variable.
The traditional metrics were completely blinded by the in-sample noise, but the critical question is, how did the CSCV engine evaluate this scenario? What did the PBO thermometer read when plunged into this freezing water?
The PBO reading for the null endpoint averaged 0.476.
A reading of 0.476, which, factoring in the Monte Carlo standard deviation of plus or minus 0.137, is mathematically indistinguishable from 0.5.
Exactly. The engine perfectly identified the lack of signal. Across the 12,870 combinatorial splits, the strategy that looked like a quantitative masterpiece in sample was equally likely to land above or below the out-of-sample median. The search procedure was diagnosed exactly for what it was, an elaborate coin flip.
Brilliant.
Furthermore, the text calculates a companion diagnostic, the probability that the selected strategy actually loses money out of sample. For the null endpoint, that probability is 0.475. If you select the best backtest from a field of noise, you have nearly a 50% chance of outright capital destruction in the real world.
The thermometer accurately identifies the freezing water. Before we look at the boiling water, though, the text includes a fascinating tangent in its honesty notes section regarding the extremes of the PBO scale. We established that 0.5 is a coin flip, representing complete randomness. What does a PBO reading of exactly 1.0 signify? Because if 0 is a robust search and 0.5 is random, does 1.0 indicate, like, hyper-overfitting?
Well, a PBO of 1.0 represents a scenario far more bizarre than standard overfitting. The authors classify a reading of 1.0 as entering a perverse region.
Perverse region.
Right. If a search procedure yields a PBO of 1.0, it means that in-sample success actively and reliably predicts out-of-sample failure. It implies a perfect negative correlation. The configurations that perform the absolute worst in the backtest will consistently emerge as the absolute best performers in the real world, and vice versa.
Wow. So if a researcher encounters a PBO of 1.0, the mathematically optimal move would be to completely invert their strategy. Whatever the backtest identifies as the best setup, they should trade the exact opposite.
Precisely. However, you cannot achieve a PBO of 1.0 by simply analyzing pure noise. Noise firmly anchors the reading at 0.5. To push the metric to 1.0, the underlying data or the strategy mechanics must contain a structural perversion.
Such as?
This usually manifests in two ways. The first is an active anti-persistence mechanism inherent in the data stream, meaning that whatever price action occurs today is mathematically constrained to reverse tomorrow.
Okay, got it. And the second?
The second, more common cause is the presence of heavy, oppressive trading costs built into the backtest engine that disproportionately penalize the most active strategies. This forces the highest turnover in-sample winners to predictably bleed capital out of sample. Absent those specific structural flaws, a total lack of edge will always return a PBO of 0.5.
Okay, that clarifies the boundaries of the metric. Let's return to the calibration and test the boiling water. The engine needs to prove it can recognize a genuine mathematically robust strategy when one actually exists.
Yes. To test the edge endpoint, the researchers constructed a new matrix M. They maintained the same dimensions, 200 columns and 1,000 rows. However, instead of 200 columns of pure noise, they injected 20 of the columns with a genuine planted mathematical edge.
A planted edge.
Specifically, they engineered those 20 columns to possess a per-observation Sharpe ratio of 0.15, which annualizes to a very strong 2.38. The remaining 180 columns were left as zero-drift normal noise.
Okay, so the environment is a haystack of 180 strands of noise, hiding 20 solid gold needles. The identical CSCV search procedure is applied to this new matrix. What happens?
Well, the search procedure analyzes the grid and selects the best in-sample performer, and the resulting annualized Sharpe ratio for the selected winner in the training phase is a staggering 3.73.
Wait, 3.73, but the true underlying edge of the gold needles was only 2.38. The backtest report's 3.73. This highlights that even when a genuine signal exists, the in-sample results are still artificially inflated by selection bias. The search procedure will always find the specific gold needle that also received the most favorable, lucky variance from the noise during the training window.
That inflation is basically inevitable. But the critical differentiator is the out-of-sample behavior. Unlike the 1.98 noise illusion that collapsed to near zero, the winner selected from the edge matrix retains a robust out-of-sample Sharpe ratio of 2.34.
Oh, wow. So it gives back the lucky variance, but it fundamentally preserves the 2.38 edge that was planted in the math.
Yes, and when the CSCV engine processes this matrix and calculates the logits across the 12,870 splits, the resulting PBO confirms the reality of the signal.
What's the number?
The PBO drops to an infinitesimal 0.001.
0.001. So across virtually every single one of the parallel universes, regardless of which 8 blocks were used for training and which 8 were used for testing, the in-sample winner consistently landed in the top half of the out-of-sample distribution.
Exactly. The search procedure locked onto a fundamental mathematical reality that was immune to the shifting combinations of time.
And the companion metric reinforces the safety of the signal, right?
Yes, the probability of the selected strategy suffering an out-of-sample loss drops to 0.00006. So the calibration is an absolute success. The engine reads 0.476 on pure noise, correctly identifying the coin flip, and reads 0.0001 on a real signal, correctly validating the edge.
Establishing the accuracy at the absolute extremes is crucial for trust. But, and I think this is important to emphasize for the listener, quantitative researchers rarely operate in environments of pure noise or absolute certainty. The strategies deployed in the real world exist in this murky middle ground.
Almost always.
And the source text addresses this reality by demonstrating that PBO is not a binary alarm system that simply flashes red for noise and green for signal. It actually functions as a continuous overfitting thermometer.
And the continuous nature of the metric is really where its practical utility lies. To map this out, the researchers used their synthetic laboratory to slowly and incrementally turn up the dial on the planted edge. They swept the true underlying edge from 0.000 all the way up to a massive 3.17, recording the resulting PBO at every single step.
And what does that look like?
The metric doesn't suddenly snap from 0.5 down to 0. It follows a smooth monotonic downward ramp.
Tracing the waypoints on that ramp really illustrates the relationship between signal strength and statistical confidence. We already know the starting point. At a true edge of 0.00, the PBO sits at roughly 0.52, and the selected strategy generates a negative 0.05 Sharpe out of sample.
Right. And then when the researchers turned the true edge dial up slightly to a weak 0.48 annualized Sharpe, the PBO ticked down to 0.44. The out-of-sample Sharpe barely crossed into positive territory at 0.19, so the procedure is slightly better than a coin flip, but it's still heavily dominated by noise.
Okay, let's look at a more realistic, modest signal. What happens when the true edge is increased to 0.95?
At a true edge of 0.95, the PBO drops to 0.21. The corresponding out-of-sample Sharpe climbs to a respectable 0.81.
Now, a PBO reading of 0.21 requires some careful interpretation. It's far below the 0.5 coin flip, but it is definitely not zero. What does a 0.21 reading actually communicate to a researcher about the fragility of their search procedure?
A reading of 0.21 indicates that the selection process possesses partial out-of-sample skill. It means that the in-sample winner successfully beats the out-of-sample median 79% of the time.
Okay, 79% is good.
It is advantageous, sure, But the 0.21 reading is a stark warning that the underlying edge is thin enough that a fifth of the time, the noise will completely overwhelm the signal, and the best strategy will degrade into the bottom half of the pack. You have found a genuine signal, yes, but it's highly fragile and highly susceptible to bad luck depending on the specific temporal window in which you deploy it.
It seems like that would require a major adjustment in position sizing. I mean, if you know that your strategy has a 21% chance of structurally failing out of sample just due to the weakness of the edge, you cannot risk the same amount of capital as you would on a strategy with a PBO of 0.
Exactly. It's a risk management tool. And the inverse relationship continues perfectly as the dial is turned higher. At a true edge of 1.59, the PBO drops to 0.03. At 2.38, we saw it hit 0.001. And when the true edge reaches an undeniable 3.17, the PBO effectively flatlines at 0.00, accompanied by a massive 3.29 out-of-sample Sharpe. A shrinking PBO is the exact mirror image of a growing, robust out-of-sample edge.
The researchers actually provide a practical rule of thumb derived from this monotonic lamp, don't they? They suggest that a quantitative strategy should be firmly rejected if the PBO exceeds 0.05.
Yes. Aligning that 0.05 threshold with the ramp data, a PBO of 0.05 corresponds to a true underlying edge of approximately 1.5 annualized. Below a true edge of 1.5, the signal-to-noise ratio is simply too low. The search procedure hasn't cleared the statistical hurdle necessary to guarantee stability. It remains way too vulnerable to the chaotic variance of the market.
But above 1.5.
Above an edge of 1.5, the PBO drops below 0.05, signaling that the search procedure has definitively locked onto a durable mathematical truth.
This continuous scale completely transforms PBO from a simple pass-fail test into an active honesty gauge for researchers. Think about it. Imagine a data scientist actively refining a model. They might decide to prune the parameter grid, alter the entry signals, or tighten the universe of tradable assets. They can calculate the PBO after every single adjustment.
Right, in real time.
Right. And if a tweak causes the in-sample Sharpe ratio to skyrocket, but the PBO simultaneously drifts higher, moving from, say, 0.02 up to 0.15, the metric instantly alerts them that they haven't improved the fundamental logic of the strategy. They've simply tightened their curve fit to the historical noise. But if a tweak causes the PBO to slide further down the ramp towards 0, they have mathematical proof that they are actually isolating the underlying signal.
It acts as an absolute safeguard against self-deception. However, and I have to point this out, discussing pure normal noise and perfectly planted edges allows for a certain level of detachment.
What do you mean?
Well, it's very easy for a seasoned quantitative researcher to look at a matrix of synthetic random numbers and just dismiss the danger. They assume they would never be foolish enough to trade pure static. They believe their strategies are rooted in deep economic intuition and complex financial logic, rendering them immune to these purely mathematical traps.
Ah, right. That wouldn't happen to me.
Exactly. And the authors of the source text anticipated that exact psychological defense. So, to shatter that illusion, they constructed a realistic trap. They designed an experiment that perfectly mimics the exact workflow executed by thousands of analysts, hedge funds, and retail traders every single day. They built the mirage of the moving average.
The mirage of the moving average. Okay, let's spring the trap.
The trap targets the most ubiquitous, universally recognized trading rule in the history of technical analysis: the moving average crossover.
The logic of the moving average crossover is just so deeply ingrained in financial culture. You track a fast-moving average, representing short-term price momentum, like a 10-day average. You simultaneously track a slow-moving average, representing the longer-term trend, like a 50-day average.
A tale as old as time.
When the fast line crosses above the slow line, it signals upward momentum, and you establish a long position. When the fast line crosses below the slow line, you exit the position or go short. It's visually intuitive and forms the basis of countless algorithmic trading systems.
And so, the researchers constructed a standard parameter grid for this exact crossover strategy. They selected 10 different lengths for the fast-moving average and multiplied them by 17 different lengths for the slow-moving average. After eliminating the invalid pairs, where the fast average was actually slower than the slow average, they were left with a grid containing exactly 170 unique configurations.
A grid of 170 parameters is an incredibly modest standard sweep. I mean, most modern machine learning algorithms analyze millions of parameter combinations. Anyone with basic programming skills and access to historical daily closing prices has run a sweep of 170 moving average combinations.
Without a doubt. But the devastating twist of the experiment lies in the data they fed into this highly logical, fundamentally accepted grid. They deployed the 170 moving average configurations onto a time series that possessed provably zero edge. They executed this strategy on a pure random walk.
A pure random walk means the data is completely devoid of momentum, trend, or mean reversion. Every subsequent data point is entirely independent of the last. It is mathematically impossible for a moving average crossover, or any strategy for that matter, to extract a predictive edge from a random walk. The underlying reality is that no alpha exists.
Zero alpha.
But the search procedure, blindly executing the grid, has no awareness of that reality. It simply churns through the 170 combinations, analyzes the historical equity curves, and surfaces the best performer.
And the aggregated results of this search expose the sheer scale of the illusion. When the researchers ran this grid across 60 different random walk matrices, the selected winner produced an average in-sample Sharpe ratio of 0.97.
An average Sharpe of 0.97 is lower than the 1.98 generated by the pure normal noise experiment, likely due to the structural constraints of the moving average rules smoothing out the variance. But an in-sample Sharpe near 1.0 is still highly deceptive.
Absolutely. And the out-of-sample performance behaved exactly as expected. The 0.97 in-sample Sharpe ticketed instantly to an average out-of-sample Sharpe of 0.04. The PBO across those 60 matrices averaged 0.463. The CSCV engine evaluated a search procedure deployed on a random walk and correctly reported a value statistically indistinguishable from the 0.5 coin flip baseline.
Okay, so an average performance drop from 0.97 down to basically zero is frustrating, but it might not be catastrophic enough to destroy an institution. However, averages inherently mask the danger of extreme outliers. And the authors isolate one specific run from the 60 matrices, a run labeled Seed 3000, that serves as the ultimate nightmare scenario for quantitative finance.
The analysis of C3000 is chilling, really. On this one specific iteration of the random walk, the grid located a fast and slow-moving average combination that perfectly synchronized with the chaotic random fluctuations of the training data. The in-sample annualized Sharpe ratio for this specific configuration was an astonishing 2.33.
Wait, a 2.33 Sharpe ratio? We are literally back at the pitch deck from the very beginning of the deep dive.
Exactly the same.
A highly logical, deeply familiar moving average crossover strategy generated a massive 2.33 Sharpe ratio entirely from a random walk. I mean, if a researcher stops their analysis at the backtest, looks at that 2.33 Sharpe, and overlays the intuitive narrative of trend following, they will deploy immense amounts of capital into a statistical ghost.
And the CSCV engine just obliterates the ghost. When the parallel universes are constructed and the out-of-sample performance of the 2.33 winner is evaluated across the thousands of splits, the median out-of-sample Sharpe collapses to negative 0.22. The strategy completely reverses from a spectacular winner into an active bleeding loser.
And what's the probability of ruin?
The probability of taking an out-of-sample loss on this exact strategy is 63%.
A 63% probability of loss on a strategy that presented a 2.33 Sharpe. The disconnect is terrifying. What was the PBO?
The PBO reading for Seed 3000 was 0.573. The authors note that the slight elevation above 0.5 is purely an artifact of sampling noise around the coin flip baseline, but the fundamental verdict remains. The search procedure possesses zero out-of-sample skill, and the source also provides the median logit for this specific winner, which is negative 0.25.
Okay, decoding a median logit of negative 0.25 reveals exactly how far the strategy fell. Applying the inverse logit formula, a value of negative 0.25 translates to a relative rank of approximately 0.44 out of sample. And since there were 170 configurations in the grid, multiplying 171 by 0.44 places the winner roughly at rank 75.
That's the tragic part. The configuration that dominated the training phase, securing the absolute #1 ranking in sample, plunged to 75th place out of sample. It failed to even maintain a position in the top half of the mediocre strategies it supposedly outperformed.
The vulnerability exposed by Seed 3000 really highlights a profound psychological flaw in quantitative research: the power of the narrative.
The story we tell ourselves.
Exactly. The moving average mirage is so convincing because it aligns with our preconceived stories about how markets operate. We have these internal narratives about momentum, institutional order flow, and trend following. When an algorithm spits out a 2.33 Sharpe attached to a moving average, our brain immediately accepts the result because it fits the story.
We don't question it.
We don't. We assume we found a genuine pattern in the market. But we fail to realize we are simply finding shapes in the clouds. The CSCV engine is immune to narrative. It doesn't care about the story, it doesn't care about the moving average logic, and it ignores the massive 2.33 Sharpe value. It just coldly evaluates the structural stability of the search procedure.
Narrative fallacy is absolutely the primary driver of overfitting. But, the text provides one final, highly specific mathematical fingerprint to identify this type of trap, the degradation slope.
The degradation slope, break that down for us.
Yep. So if you take the data from all 12,870 combinatorial splits and plot them on a scatter chart, placing the in-sample Sharpe ratio of the winner on the x-axis and its corresponding out-of-sample Sharpe ratio on the y-axis, you can calculate a linear regression slope. For the moving average Mirage and C3000, that degradation slope is negative 0.92.
A degradation slope of negative 0.92 is virtually a one-to-one inverse relationship. It implies that the better a specific moving average configuration looked during the in-sample training phase, the worse it performed in the out-of-sample testing phase.
And that aggressive negative slope is the undeniable signature of overfitting on a time series with memory.
Why does it happen so aggressively?
Because the moving average rules are latching onto transient, localized patterns within the specific training blocks. Because the underlying data is a random walk, those localized trends are statistical anomalies. If a random series trends heavily upward in one block, probability dictates it will eventually reverse or flatten out. The harder a specific parameter combination fits that localized anomaly, the more violently it crashes when the anomaly inevitably reverses out of sample.
But wait, that aggressive negative slope introduces a major point of confusion for me.
Oh.
Yeah, during the calibration phase, when we were discussing the genuine planted edge of 2.38, the text noted that the real edge also exhibited a negative degradation slope, specifically negative 0.52. If both a massive overfit mirage and a genuine robust edge display negative slopes when plotted across the combinatorial splits, how does a researcher tell the difference between the two?
That's a great question. It requires separating the direction of the movement from the final destination.
Okay, unpack that.
Well, a negative slope is practically universal due to the law of regression to the mean. Even when a genuine, powerful signal drives a parameter grid, the specific configuration that secures the absolute top spot in sample likely benefited from a small degree of favorable noise layered on top of its real edge.
Right, it got a little lucky on top of being good.
Exactly. When that configuration moves out of sample, the favorable noise evaporates, causing its performance to drop slightly. It regresses. Therefore, a real edge will show a negative slope because it inevitably shrinks.
So the slope simply confirms that shrinkage is occurring, which is a mathematical guarantee in almost any optimized search.
Yes. The critical differentiator is not the shrinkage itself, but where the strategy lands after the shrinkage has occurred. The genuine edge shrinks, but it remains anchored by its fundamental signal, keeping it near the very top of the out-of-sample rankings. Its PBO remains 0.001. The moving average Mirage, lacking any fundamental anchor, shrinks catastrophically. It plunges from first place down to 75th place, landing squarely on the coin flip line with a PBO of 0.5.
Okay, I see. A real edge is like a reigning champion who might stumble slightly in a new arena, but still easily dominates the competition. The Mirage is a spectator who found a weapon by chance, won a single skirmish, and is immediately destroyed when placed in a real battle.
Exactly. The mechanics of regression ensure that the in-sample peak is almost always a localized maximum, but the PBO determines the elevation of the floor it falls to.
The introduction of PBO profoundly challenges the utility of older industry standards. I think the final act of this analysis requires uniting this new engine with the traditional tools of quantitative finance, specifically the Deflated Sharpe Ratio. We need to understand how they interact, where they diverge, and how they can be visualized geographically through the concept of plateaus versus spikes.
And it is crucial to understand that the Deflated Sharpe Ratio, or DSR, and the probability of backtest overfitting, PBO, are not mutually exclusive or competitive metrics. They are complementary halves of a comprehensive honesty check. They serve different functions because they interrogate entirely different mathematical objects.
Okay, break down the division of labor between the two metrics.
The Deflated Sharpe Ratio puts the winner on trial. It approaches the problem parametrically. DSR asks a very specific question. Given that you ran exactly n different trials in your search grid, is the specific Sharpe ratio of your single winning strategy high enough to prove it wasn't just a product of multiple testing luck? DSR requires the researcher to explicitly know the number of trials they ran, and it uses that number to mathematically inflate the threshold of statistical significance the winner must clear.
And the text highlights a severe vulnerability in how DSR handles that calculation, particularly when applied to standard parameter grids.
It does. The vulnerability stems from the assumption of independence. DSR can be easily distorted by a highly correlated grid.
Give me an example of that.
Consider a parameter suite testing 640 different moving average combinations. Many of those combinations are virtually identical in their behavior. A configuration using a 10-day fast average and a 50-day slow average will produce a return stream almost perfectly correlated with a configuration using an 11-day fast average and a 50-day slow average. They are not independent ideas.
Right.
However, if a researcher feeds the raw number 640 into the DSR formula, the math treats them as 640 completely independent orthogonal trials. It severely overpenalizes the winning strategy, inflating the noise ceiling unnecessarily high and potentially causing the researcher to reject a valid signal.
It counts 640 unique suspects in the lineup, when in reality, 600 of them are just slight variations of the exact same suspect. It artificially raises the bar for proof.
PBO circumvents this vulnerability entirely because it puts the procedure on trial rather than the winner. It asks whether the act of picking the best generalizes. Because PBO utilizes the non-parametric CSCV engine, which physically resamples the empirical return matrix rather than relying on abstract probability distributions, the correlation within the grid is handled natively. The engine simply observes how those highly correlated columns behave across the 12,870 splits. It never requires the researcher to manually quantify the number of independent trials.
So DSR evaluates the magnitude of the winner, and PBO evaluates the stability of the procedure. The source text explicitly advises researchers to run both metrics. I can see why. A search procedure might yield a very low PBO, proving that it is genuinely locating the best available signal and generalizing perfectly. However, the absolute Sharpe ratio of that genuine signal might be a 0.2, which is robust, but too small to profitably trade after accounting for transaction costs. DSR would alert the researcher to the lack of magnitude, while PBO validates the logic.
The synergy between the two metrics is undeniable, but it forces a deeper question regarding the architecture of the grids themselves.
Oh, what's the question?
Why does resampling the historical data across 12,870 combinatorial splits expose the mirage of the moving average so effectively while validating the true edge? The authors provide a compelling geometric intuition to explain this phenomenon, distinguishing between topological plateaus and isolated spikes.
I have to say, the geometric mapping is the most clarifying visual concept in the entire analysis.
It's beautiful, really. Imagine plotting the performance of every single parameter combination on a three-dimensional topological map. If a genuine fundamental economic effect is driving the profitability of the grid, the successful parameter configurations will cluster together geographically.
Right.
If a fast length of 3 and a slow length of 55 captures the structural anomaly in the market, then 4 and 56 will likely also capture it, as will 2 and 54. They're all tapping into the same robust underlying physics. On the topological map, this clustering of high performance creates a broad, highly elevated plateau.
And the structural integrity of a plateau makes it inherently robust against the resampling process of CSCV.
Exactly. When the CSCV engine generates a split, it selects 8 specific blocks for the training set. Regardless of which specific combination of 8 blocks it selects, the in-sample winner will almost certainly be drawn from somewhere on that massive plateau. And because the plateau represents a genuine, persistent market reality, that entire region of the grid will remain elevated when evaluated against the out-of-sample test blocks. The 12,870 splits will largely agree with each other on the general location of the optimal parameters. Massive agreement across the splits yields a PBO approaching 0.
But the topology of overfitting the mirage is violently different.
Overfitting manifests on the topological map as a lonely, isolated spike. It is a single specific cell in the parameter grid that, through sheer mathematical coincidence, happened to perfectly align with the random noise present in one specific combination of training blocks. It possesses no structural foundation. It is surrounded by mediocre, completely worthless neighboring configurations.
And the isolation of the spike basically guarantees its destruction during combinatorial cross-validation.
In split number 1, the unique arrangement of the 8 training blocks might elevate that specific spike, crowning it the winner. But in split number 2, which uses a slightly different combination of training blocks, the noise profile completely changes. The first spike vanishes into the terrain, and a completely different, equally lonely spike located somewhere else on the grid randomly becomes the winner.
So they keep shifting.
Right. None of these isolated spikes can survive contact with the out-of-sample data blocks. The 12,870 splits fundamentally disagree with each other on what constitutes the best parameter. Total disagreement across the splits yields a PBO of 0.5.
Envision dropping 12,870 paratroopers out of an airplane at night, right? Scattered across a vast mountain range, and instructing each of them to find the highest ground. If there is a massive continent-spanning plateau, a genuine structural edge, the vast majority of those paratroopers are going to navigate toward that stable elevation. But if the terrain is entirely flat, punctuated only by incredibly thin, jagged, random spikes of rock, which is the definition of overfitting, each paratrooper might stumble onto a different jagged spike in the dark. They will all radio in and claim to have found the summit, but when the sun rises, they will realize they are standing on isolated, fragile anomalies.
That's a great way to picture it. And the combinatorial symmetry of the CSCV engine essentially forces the sun to rise 12,870 times. It exposes the fragility of the spikes in a way that walk-forward optimization never could. A single spike can survive one arbitrary walk-forward cut simply through luck, but a spike cannot withstand the exhaustive interrogation of symmetric resampling. PBO systematically differentiates the plateau from the spike across every possible iteration of the data.
The implications of this framework fundamentally alter the burden of proof in data science. We opened this analysis staring at a pitch deck presenting a pristine 2.33 Sharpe ratio. We now understand that without subjecting the search procedure itself to the combinatorial stress test of PBO, that 2.33 metric is worse than meaningless. It is an active mathematical hazard.
The foundational takeaway is a reversal of standard presumption. The winner of any algorithmic search is unequivocally guilty until proven innocent. You cannot trust a backtest by evaluating the smoothness of the equity curve, the size of the final Sharpe ratio, or the intuitive logic of the underlying rules. The metric used to optimize the search secretly dictates the vulnerability of the strategy. A simple one-bar look-ahead bias can mathematically manufacture a Sharpe of 15 out of thin air. A multiple testing parameter suite can manufacture a 1.98 Sharpe from pure noise.
Only a symmetrically resampled selection procedure can expose the worthless winner that traditional metrics inadvertently crown. The probability of backtest overfitting is the ultimate lie detector test for the quantitative researcher. It is the only mathematical guarantee that you have not simply isolated the luckiest coin in the auditorium.
And the practical application for anyone working with data is clear. Pair the probability of backtest overfitting with the deflated Sharpe ratio. Interrogate the magnitude of the winner, but ruthlessly interrogate the stability of the procedure. Demand mathematical proof that your search has located a plateau and reject the spikes.
As we conclude this deep dive, I want you to step back from the highly specific world of algorithmic trading, moving averages, and financial parameter grids. Consider how frequently we run exhaustive, undocumented search grids in our daily lives without ever recognizing the mathematics governing our decisions. When a marketing department A/B tests a new campaign across 20 different demographics, they are running a parameter sweep.
Yeah, that's true.
When you experiment with 50 different diets, supplement routines, or workout programs to determine which one makes you feel optimal during one specific month, you are executing an in-sample training phase. Even the act of swiping through 1,000 dating profiles until you find a connection that feels perfectly aligned within a narrow window of time is a form of selection bias. In all of these scenarios, we isolate the winner that happened to perform best in our limited historical experience. We crown the victor, and we immediately construct a post hoc narrative to explain why it makes a perfect logical sense.
And tell ourselves the story.
But if a combinatorially symmetric cross-validation engine could somehow be applied to the dataset of your own life choices, if a PBO score could evaluate your personal decision-making procedures, how many of your deeply held winning strategies would be exposed as nothing more than an exhaustively searched coin flip? How often are you standing on a jagged spike of noise, waiting for the out-of-sample data of reality to pull you back to the median? Something to think about.